Hello and welcome back to the Machine Learning at Microsoft YouTube channel. It's a very good place to be. Today is a very special episode because it's the first of a series, a brand new series, which we're going to call paper review calls. I've launched a series of calls internally at Microsoft in my group at Commercial Software Engineering, and these calls are an opportunity for a data scientist or a software engineer to choose any paper that they want in the machine learning literature and to spend an hour talking about it to all of us. They can choose anything they want. They can talk about the current context of the paper in the literature. They can talk about the method, the results. They can interpret the results. They can do an implementation. They can do some PowerPoint slideware. The flexibility is there, but it's an opportunity for all of us to get skilled up on machine learning by reading papers. And reading papers is a really difficult thing to do because papers are complicated and no one can read a paper from start to finish and understand all of it. There's always a lot of cognitive dissonance there, and you're wrestling in your mind with things that you do understand and things you don't understand. And it's a really, really challenging thing to do. And it's something that we should encourage and pressurize ourselves to do, but in a friendly and inclusive atmosphere that isn't judgmental and isn't elitist in any way. Anyway, my friend, my partner in crime, Eric Schles, who's a data scientist from New York, he has stepped up to the plate and he is doing the first one of these paper review calls. So kudos to Eric. He's chosen a really interesting paper which was released pretty recently actually, so it could turn out to be a hugely seminal paper, we don't know yet. And the main premise of this paper is, wouldn't it be interesting if, at the moment when we solve neural networks, when we do forward and back propagation, we use a two-dimensional data structure, a matrix, and this new paper suggests that we could use a higher dimensional data structure. We could use tensors, and in the paper they use three-dimensional tensors. And it has some really interesting properties because you can learn some powerful representations that actually seem to model correlations in higher dimensions. And also there are some computational advantages as well. Because of the way that you store the data, you can actually use a discrete Fourier transform, and as an extension of that, the fast Fourier transform. And the fast Fourier transform and the time complexity sort of becomes increasingly linear as n gets smaller. So this is an algorithm proposed that has really, really good computational characteristics. It has really, really good convergence characteristics, and it also has incredibly good predictive power on several data sets were tested, MNIST and CIFAR10 for example. So this is a potentially really interesting place for neural networks to go. What I also found personally interesting is that this method seems to work so well on vision problems, even though essentially it's a form of, it's modeling a fully connected layer in a neural network. But anyway, without any further ado, I hope you enjoy the call. I'm really interested in your feedback, so don't forget to like, comment, and subscribe, and we'll see you back next week. Fantastic. Okay, so we're recording now, and Eric, would you like to introduce yourself and what are you going to be talking about today?
Yeah, so sorry, give me a second. Switching between lots of screens. You're going with video. Oh no. I guess should I go with video?
Oh, yes.
Okay, I'm doing
yes.
it. Oh no, I didn't comb my hair. Hi, I'm Eric. So I've spent a lot of time working on this talk. I think it's gonna be super fun for everyone. The slides are mostly done. I'm going to be jumping between slides, a markdown file, and unfortunately the internet a little bit. All the visuals are there. The only problem is there's specific pieces that just didn't make it onto the slides because this paper is so dense and so thick, and I try to understand as much of it as possible. And so I'm going to try to do as genuine a presentation of the paper as I can. And so a few things will be missing, but we're going to do what we can. This is supposed to be fun, and I'm going to try to make it as fun as possible. Okay, I'm going to share my screen and get started. And you can see the mess that is my desktop. Racing to the last moment. Okay. So let me go into presentation mode and let me pull up my speaker notes so I don't say the wrong thing, because math is hard, and if you don't explain yourself super well, everything is crazy. Okay, so before I start talking about the actual paper, I thought I would do a little riff on algebra and what it means. So the notation of an algebra should appear familiar. But it is worth it to formally define the notion of an algebra. An algebra is about setting up a set of primitives and a set of operators as a mental model for the interworkings of a system. By defining said system in algebraic terms, we can make use of a minimal set of primitives and operators to mimic the complex realities of the semantics of a system. In doing so, we reduce the mental load on those conversing about the system and allow ourselves a language to discuss how the system works in clear and minimal terms. To put it bluntly, defining a system in algebraic terms is the same thing as defining it, if done correctly, in clear and obvious terms. So it's basically about good writing, about clear terminology, about clean and simple prose. And you can have lots of primitives and lots of operators, but often it is possible to decompose operators such that we can end up with a minimal or basis set of primitives and operators. And so in doing so, we define our minimal set of primitives and operators such that we are able to actually fully understand what's going on and not have to deal with all this mental load. So there's a lot of notation here, and it's sort of like a joke, right? Like, you want to have as little notation as possible. That's what algebra really strives for, about having the right set of primitives and the right set of operators such that you can describe any system sufficiently well. So at the end of the day, doing algebra is about communicating well and about fully specifying systems such that deterministic rules can be made use of to understand what happens under certain circumstances. So imagine for a moment an algebra for the stars, or for a Rubik's Cube, or for juggling, or for the elementary particles of the universe. By defining algebraic primitives and operators, each of these systems then becomes clear and very inviting. And you can do a whole bunch of stuff. So we're going to be defining essentially some algebraic terms for these higher order tensors that we're going to be looking at in this paper. And there's a clear and natural association between the systems I just described and the algebra we're going to define. And I believe my hypothesis, and the hypothesis of the paper, is that this is why we're able to get the performance gains that we'll see at the end. It's because of the way in which the algebra is described and the operators and the primitives that we make use of in order to do it. Okay, so without
Eric, can I just quickly interject? Could you just spend about a minute just saying what is the paper and what are the high level findings of the paper?
Yeah, so the paper is called, the name of it is long, so I'm going to just have to recall that for a second. All right, so the paper is named Stable Tensor Neural Networks for Rapid Learning. And the basic notions that this paper purports are as follows. They propose a tensor neural network. So we'll see this is the same but different than normal neural networks. The reason it's the same is because technically matrices and vectors are tensors, but we're going to be dealing specifically with higher order tensors. So these are order 3 tensors in this case, but the paper states that you can generalize this to higher order tensors, so order 4 or order 5. If you don't know what those words mean, don't worry, we're going to explain it. So basically they make use of these tensors and they're able to show they get better performance on Cephere and MNIST. And they do this by taking advantage of the by extracting multidimensional correlations that would otherwise be latent in traditional algorithms. The other thing that the paper sort of comes to is that you can use a tensor to matrix multiplication called the T product rather than the traditional matrix to matrix multiplication. And so you get a relatively minimal tensor product, and so you're acting on far fewer elements than you would with the traditional neural network setup. So yes, we're dealing with a higher dimensional space, but at the same time, we're actually like in a smaller representation of that space because of the mental model of order 3 tensors.
And just quickly, Eric, when you say it performs better, it has a better predictive performance and it also converges faster. So it's better from a, computational complexity point of view.
Indeed. There was another question, it sounds like.
No, I think that was me. Tim asked the second part of the question that I wanted to ask if it's computationally efficient. So we're good.
Okay, cool. Oh man, everyone's on video today, setting a new precedent. I really should have combed my hair. Okay.
Oh, you look lovely, Eric.
Oh,
Yeah,
thanks.
I'm still in my PJs if you can't tell, but
Oh no, I can't. Okay, all right. So let's move on. So why? Well, we've sort of answered it already, but why order 3 or higher tensors? So let's first of all recall the motivation for a matrix or a tensor of order 2. So we have a system of equations. In other words, we have a single equation that does not uniquely account for a full possible set of states of a real world phenomenon. So let's say that we had supply and demand, for instance. We would need 2 equations because supply and demand both are defined by quantity and price. Those are the 2 variables that we would consider. And so in this simple example, right, we need an equation for supply and an equation for demand. So each equation defines the semantics of part of our system. And so we need both of those equations to get the interactions of the system such that we define this, this unique solution that clears the market and creates equilibrium. So it's not any different when you're dealing with tensors of order 3. The motivation is slightly different semantically. The motivation is what if the equations depended on more stuff, right? So same idea, slightly different. So I'm going to sort of talk at you for another minute, and then I'm going to start walking through some examples. So one way we can define order 3 tensors is by constructing multi-indices. So there's some, I'm going to go over a simple mathematical explanation, and then I'm going to walk through how we would define an order 3 tensor. Perhaps not in pandas itself, although we could do it, but it is possible. So assume we have a data set which includes information on supply and demand like before. And now we're going to further assume that demand can be defined by whether or not a person is a smoker. Now, let's say we want to calculate the supply and demand behavior for the entire economy, smokers and non-smokers. Will the equations be the same? The claim that I'm making is probably not, because smoking suppresses appetite, so demand for food will likely be lower. Also, smokers tend to have more health problems later in life, so the demand for medical attention will likely be different. So this means there are likely sizable differences in the demand and supply equations for smokers and non-smokers. Now, this is just one segmentation. We could do many segmentations and thus creating many sets of equations that define our model. And so naturally, we have this tensor by taking, well, we'll see how this is done, but we can take a vector times a matrix, and that is how we naturally arise to an order 3 tensor. It's about having a segmentation or a set of classes, and then having some typical traditional matrix that defines a set of equations. So hopefully that motivates it well. Here's how you would slice said tensor. Now we're going to look at some examples if all of that was over your head. So we're going to introduce some trivial examples, and then we're going to look at them in different frameworks. So the first one, oh, sorry, we will look at a pandas example. I apologize. The first one we're going to look at is in NumPy. So this is obviously the simplest possible example. You just start with an array, and then you just reshape it and say, okay, I want a 3 tensor. And you can do so easily by saying 10, 10, 10. Notice that these 3 tens multiply to 1,000. Otherwise, you can't do this. So you get a natural number shape. Now, unfortunately, NumPy doesn't come with a ton of operations on tensors built in the way PyTorch does. There are actually quite a few. If you go throughout the landscape of SciPy and NumPy, you can define quite a bit of operation on order 3 tensors. And in fact, we'll be using some of the NumPy order 3 tensors because they're operations, because they're not defined for PyTorch later. So here we can see a semantically motivating example, because just working with random numbers doesn't really provide much value to us. So we can see an order 3 tensor through the multi-indexing scheme. Now remember, I said smokers and non-smokers before. That was for this reason, because this is the TIPS data set and they make use of this. And so we're able to create this order 3 tensor by simply looking at a multi-index approach. And you get some niceties within pandas. You can, and it comes out sort of obviously from a group by. You can swap the level, which switches here and here. So the previous one, as you saw, there's time and then smoker. Here, time is first and then smoker is second. And likewise, we can do we can flip across the axes, so we can make an index by row the same as a column. Okay, so this is going to be the tensor that we're going to make use of throughout this talk for the most part. Sorry, I saw PyTorch and my brain just went nuts. So we have a tensor operator. It's naturally defined. We can just pass things in an obvious way. And so we don't have to do this thing where we reshape our array, which is really nice. And this is one of the advantages of using the PyTorch tensor over the NumPy tensor, is that you can just explicitly pass your equations. You don't have to do any reshaping weirdly, and you have some guarantees around how your shaping is going to happen because you can be more explicit about it. And then we sort of can validate the slicing works. Now, of course, this isn't validation in itself, and I'm going to explain how slicing works and everything else if you're not familiar, or in the 3 space if you're not familiar. Okay, before we go through slicing, let's do a brief digression into Einstein summation notation. The reason why I'm going to introduce this is because we really want this outer product, which is the reason why it's first. Outer products are super cool, and they're what we're going to use to define our vector to matrix multiplication. But also, we can do all of this crazy stuff for free, and this isn't even a full set. There's so many things you can do with Einstein notation. It is the coolest thing by far that I learned reading this paper. Well, not the coolest thing. They're all cool, but this is pretty great. Okay, so first we're going to start off with a simple example. Sorry, this is kind of cut off. I didn't really do this the best. It's a little awkward. But anyway, so we have a matrix that we want to transpose, and it's currently in ij, and we want to turn it into something ji. So we want to flip across the diagonal. We can do so in a really obvious way by just literally specifying, the semantics down here. So basically, this ij, right? This semantics. You can name these variables whatever you want, but basically this acts on the rows and columns of your tensor. So if you had a tensor in 3 space, which we'll see soon, you would just specify another variable. But this is clear and obvious and really, really simple. And then we just say what we want to happen to the matrix on the other side, specifically by only thinking about the abstraction with respect to the axes that we're going to operate on. So this is a really powerful notation. Here we have to pass in A as such. So it's just that simple, though. We can see another example, slightly more worked, with matrix multiplication. So sums are sort of implied in Einstein summation notation. Excuse me. So here we have a summation. It's implied, right? We take I, K, K, J. So there we have I and K and J. So these are the things that we're going to be multiplying across. And then it's implied that we're going to do the sum and multiplication over these things, and we end up with just the ith jth row. So that's this and this, right? And so
Eric, in the previous example, though, the summation was a no-op, right? Because you're just transposing one single matrix.
Yes.
Okay.
Yeah. So it's interestingly, the notation is aware of it understands the semantics of what you're doing in a really flexible and obvious way, because it's such a restricted set of things. So it is a no-op in this case, correct?
And this DSL that you have within quotes, is this defined in the paper, or is this somewhere else? Because
No. So Einstein notation is a well-trod thing. It's used throughout. So there's interfaces for it in PyTorch, in NumPy, in TensorFlow. It's a really powerful, really flexible notation for defining operators with respect to tensors.
Yeah, this is pretty cool. Yep.
Yeah, it's a really good DSL. And we're going to see it get used to define the outer product because there wasn't a good outer product for 3 tensors already defined. But now with Einstein notation, summation notation, we can define tensors of any order and the operators that we might be interested in an obvious, clear, and straightforward way. We just specify the variables. We understand how the columns and rows, or in this case, the axes, transform within our tensor, and then it's obvious to manipulate them. So this is, I think, Einstein's true claim to fame, and it sort of shows the genius of the man because this is such a clear and simple DSL. Before DSLs were even a thing, right? So that's kind of fun. Okay, so here we have it. Without any further ado, the outer product defined for us over 2 and 1 space to give us 3 space. So here it's like pretty obvious that we're going to order 3, right? Because we start with I, J, comma, K, and then we just sort of bring things along, and it just does what we want it to. This is kind of wonderful because it's so obvious and simple. And now we have an even more semantically compact way of defining our order 3 tensors. We specify our classes here, and then we have the operations that it's acting on, the equations that it's acting on over here. And now this is as clear as day.
Hey, Eric, quick other question. So in this case, the vector is 3 by 1. What if the vector was 1 by 3? Would it transpose it automatically to make a valid product? Or
I didn't try that.
Okay.
I don't know.
Sorry. just
I
curious.
don't know. I have no idea.
Since it does so much magic.
Yeah, it probably does. My suspicion is it would, but like this is very magical. This is very magical. Oh, you can't have any spaces. It was not obvious that if you have spaces, then it's going to yell at you. You can't have any spaces in the DSL. So notice none of these examples have spaces between our things. It's very important that you don't have spaces. Anyway, okay. So interacting with tensors in order 3. Unless there are more questions. Okay. Yeah. All right. So the traditional one-dimensional case, I'm more going over this for just completeness, but we should already know this. Basically, we can start by defining and selecting the 0th element, right? So that's just indexing as normal. We can define a colon within our index to create a slice. So this goes from the 0th to the 10th element. And we can, in fact, define a copy by just looking at all the elements and just putting a colon there and not specifying a start and stop. Additionally, we can specify a jump. So in this case, it's reversing it because we specify -1. So it starts at the end and then goes to the beginning. Here we specify every second element. So it goes 0, 2, 4, 6, so on and so forth. Here we can get every third and so on and so forth. And we can go negative or positive in the order, in the direction that we index. So that's pretty cool for single dimensional slicing. So in the 2D case, we can define subsections of our matrix or sliding windows in 2 space by just specifying the start stop across each column. So this is the row and this is the column for the 2-dimensional case. So we can obviously select individual elements and so on and so forth. Now here's where things get really fun. So if we want to copy, it's pretty simple. We specify each of the axes and we just say, give us everything. Okay, cool. We know how to copy things. That's really neat. Well, it turns out that we can actually do something that comes to us through the paper in a really obvious way. So if you recall, the frontal slices, the lateral slices, and the tubal slices. Here we hold one thing constant, here we hold another thing constant, here we hold 2 things constant. In Python, with slice notation, this is as clear as it's ever going to get. We simply say, okay, give me everything and then fix this. Give me everything and then fix this. Okay, just fix these first 2 things and then I get a tube. Now notice we can get tubes across any one of these axes, but we just sort of pick the third one arbitrarily as the one that we'll tubal slice across. So that's pretty cool, right? Like that's going to be a major conclusion of this paper and everything. Yeah.
So I have I don't know if it was if others were thinking about it as well, but if you go back to that diagram that you had in the front of the different slicing mechanics, right? In my limited sort of view, this maps straight to convolutional nets, right? Because this is what you do in convolutional nets. You take an image, you apply a filter, you get an activation map that looks like a cube, and then you carry on from there on.
Not quite.
Not quite. Okay.
Not
Not
quite.
quite.
Is the
I
answer.
think this is a direct replacement for densely connected layers in a neural network. But before, you would represent them with a 2D matrix. And now you represent them with, in this case, a 3D tensor, but it could be even more dimensions than that. And I think that the goal of the paper is twofold. First of all, by having this highly dimensional structure, you can learn latent high dimensional representations in the data in a way which you couldn't do before, but also the time complexity of, the convergence properties are so much faster. And the reason for that is when you take this so-called tensor product of these data structures, you can use the discrete Fourier transform. If you take the discrete Fourier transform of both of these tensors, and then you multiply them together, and then you take the inverse Fourier transform of that. It's basically the same as doing this tensor product, and it means that the fast Fourier transform has a log linear time complexity, so it's significantly faster than doing it directly. So I think that's kind of where the paper is going, is that by representing these structures in this way, you can have these advantages.
Does that answer your question?
Yeah, I'll have to. Yeah, I'm assuming it did.
Okay.
Well, I mean,
we'll think about it. We'll think about it.
Just quickly, Jet. I mean, I think I missed one important thing that you said, is that this seems a bit like convolutional neural networks, and it isn't. We are using something called circulant convolution. Yeah. We're storing this data in a circulant matrix. But what's really interesting is at the end of the paper, they actually test this on vision data sets. They test it on CIFAR10, for example, and it seems to perform better than the state-of-the-art convolutional neural networks. And this is effectively a densely connected network, but structuring the data in more dimensions. So it's learning some kind of latent higher dimensional representation, and it seems to be doing a better job of image data than CNNs, which is very strange.
Okay. Yeah.
Well, I have a theory on that, which we'll get into.
I'll be candid. I haven't read through the entire paper, but yeah,
Don't worry.
I gave up when they started talking about Hamiltonians. My math was getting a little stretched, but
we're not going to go through the Hamiltonians.
Yeah, I think the point that I was trying to make is in the early part of the paper where they were sort of establishing the algebra part of it, right? Before they went into the actual network part of the paper. As I was reading through it, and I thought about the sort of the intermediate representations of data in a convolutional neural net. A convolutional neural net is yeah, sort of, right, exactly. So the intermediate representation of the data is essentially, as you go through layers of a CNN, you're changing dimensionality, but it's a three-dimensional representation of data, right? So it's
still two-dimensional. But what happens in a convolutional neural network is in every single layer you are learning convolutional filters as part of the training process. But in forward propagation, you're actually outputting a response map for every single convolutional filter. So right. you in that sense you do learn a kind of three-dimensional data structure, because it's response map times
the number of filters, right?
Yeah, exactly.
Yeah. Right. So that was my mental map, but maybe that's wrong. Okay, got it.
But I think the difference is in a convolutional neural network, you're actually, because basically it transforms data out of the space domain, and you're kind of you're learning something about how these like local spatial kind of dependencies in the input space. And I'm not really sure how. I mean, presumably this must be doing the same thing in a different way. I mean, what do you think, Eric?
So, I'm worried that we've gone too far afield and we've lost people.
Okay.
Sorry about that.
I mean, We can keep going. Do we want to keep going?
Yes, please. Don't let my question disrupt it. Let's
Well,
just.
so I think it's a valuable one, and we should have this discussion. But like, I'm worried that some people who maybe have less of a background will feel excluded. But okay, fine. So we will talk about this at the end. How's that? Is that
That's
fair?
fine. That's
Okay,
perfectly fine.
cool. Okay. Because I think this is a healthy debate, and it's the central conflict in the paper is like, what the hell is going on, right? So okay, returning to Einstein notation. Um, blah blah blah. Lost my spot. Okay, yeah. So okay, so we've seen how to do this multiplication, and now we can even define a tensor product using order 3 things really easily, right? So we simply say, okay, these are the columns that we care about. Oh, cool. Now I just have this. This is great. So I don't actually need the fast Fourier transform to define one. Now, what Tim was talking about is I need the fast Fourier transform if I want to do this efficiently, but I can certainly just come up with an Einstein summation notation approximation for this, and it'll work. It's not good, but it'll work. I mean, it's good enough, but it's not fast Fourier transform good. So one of the things, and I think this is where my slides die. Yeah, this is where my slides die. So now we have to go over to the notebooks. Oh no. So you'll see my speaker's notes, unfortunately. But let me make this bigger.
I mean, just to motivate this, it might be worth showing in the paper on the first page, they have what's the formula for neural networks.
Yeah.
And it's like a W dot A.
Yeah,
So
yeah.
just show that. So on the very first page,
On the very first
there's
page.
so it shows you, to calculate a fully connected layer.
Oh, this guy,
You
yeah.
need this. So an activation, and W and A are matrices. They're two-dimensional. And then a tensor neural network, if you just scroll down to the top of the next page, is basically the same thing, right? But W and A
Yes.
become tensors, and
Right.
this dot becomes a tensor product. And this tensor product, if you just scroll down to the top of the next page and then go to the bottom.
No, I think
Yeah.
oh, you mean the BCirc? Okay.
Well, the
You're
let's
talking
just
about
look at
the
let's look
picture,
at the
right?
tensor product first. So if you just go to the top of this page,
Okay.
so the just go down a tiny bit.
This one?
Down a tiny bit more. Just
Oh,
yeah.
this.
So this is the tensor product. So the tensor product is A and this sort of asterisk symbol B, and it's when you fold and then you take the block circulant matrix times the unfold of B. And so this is something which you could compute manually, but weirdly, if you take the discrete Fourier transform of A and B and then do the IFFT, it's the same thing. And that's because when you do a discrete Fourier transform of a circulant matrix, it actually does a whole bunch of Fourier transforms down the third dimension. It diagonalizes the matrix.
So I implemented this just to show you. This is the BCirc, so this is my implementation of it. I kind of stole this from MATLAB implementation. And then we can actually look at the T product. So this is what Tim is talking about. Here we're going down the third dimension by using this fast Fourier transform over n dimensions. So here we don't have to specify that it's the third dimension because this is how we do that. And then this is so this conjugate stuff that's happening down here. This is this stuff here, right? So we're able to directly see. Well, this whole thing is the same thing as this, but we're able to see directly how this fast Fourier transform comes out through the T product, right? So these are the fast Fourier transforms being done and being operated on. In clear and obvious terms, right? So yeah, sorry, just filling in.
So I suppose that the take-home message here is twofold. Using the fast Fourier transform is significantly faster than doing traditional matrix algebra, and secondly, having the data structure in 3 dimensions allows it to learn really powerful parameterizations in a sort of higher dimensional space than it would otherwise have learned. So it's actually, it's even though you might have less parameters in your model, it's actually learning more powerful representations that generalize even better.
Yeah, which is super great. So continuing forward, we have a few other little things sort of mucking about. So one of the things that we need as a primitive for this, so now that we have the T product, is we need invertibility and we need a notion of transpose and we need a notion of identity. So transpose is actually quite trivial to implement. We can simply just do numpy.transpose because there's a natural bridge between PyTorch tensors and NumPy. And so we can just use NumPy operators on order 3 tensors when that makes sense. And this will work, which is like pretty awesome. It's like one of the best things about PyTorch is its interface into NumPy in an obvious, straightforward way. You just call NumPy functions. So cool. And then the other thing we have to define is the identity. So by being able to define an identity, and here's how we do it. We simply say, okay, we'll take the M cross M identity matrix on the first frontal slice, and then everything else is just zeros. And so that's pretty easy to define. We can do that right here. So we just have our 3 dimensions, right? We, get our I, which we just, again, steal from NumPy. And then we're able to just implement, we just append our zeros, and then we just turn it into a tensor. So NumPy, the interplay between NumPy and PyTorch save us yet again. And so the last thing that we're not going to show, because it's outside the scope of this paper, I think in true sense, is the invertibility of this. So we can assume that if we have an inverse and there's a notion of of identity for our matrices, then we have some invertibility and we can define it as such, right? So the T product does allow us to define some matrix that inverts A or like A to the -1. We don't care what it is for our purposes, but it does exist because we can define our identity in this way. And so now we're actually in fine form to define, as Tim was talking about earlier, which is like super great from this paper. We have the traditional setup for a neural network, and we can just move over and generalize out to tensors of order 3 or higher with essentially the same notation. So the tensor loss function, we can just do least squares, and it's just least squares over the tensor, or we can actually do a cross entropy loss function, which is like pretty easy to do. So we can define a soft max, and then we can just do that over the scalar tuple. Now remember, the tuple, well, actually there's a nice picture right below it, so I'll just stay with this. The tuple is this thing. It's like these vectors, these vector of tubes, right? These tubes here, and then we simply define our cross entropy down in here. So here's our cross entropy loss. And we just define it in the same way. So notice, this is like the standard way that we define cross entropy loss, and it just comes out naturally. So we have our softmax output layer. Softmax is our activation, and then we output that for classification to this cross entropy loss function. And we just get it naturally because these tensors are just a generalization. So now we're in good form to be able to think about backpropagation. Now, I did not implement this piece of it. I do not have any code for this because I thought I would leave it as an exercise to the reader to actually do that for yourself. So I'll just walk through some of the notation that I think you'll need in order to do that. One of them is the Hadamard product, which actually is pretty easy to implement. So you can use Einstein summation notation to do that over tensors. So there's a reference at the end, which I won't pull up now, but gives you Hadamard product. It's the element-wise product. And then the transpose we have to find. I've shown you how to do that already. The derivatives obviously still need to be decided upon. Summation is trivial because we have the Einstein summation notation. And so you're able to decide on you can define all these operators, and then you can just define your backpropagation in normal sense. If you're interested in implementing this yourself, one of the things I would recommend is the neural networks from scratch. I really like this notion, and my favorite one is by Trask. So Andrew Trask does a great job explaining neural networks and how to implement them. And so you can take, because remember there is this bridge between NumPy and TensorFlow, or PyTorch, you can just take this code, and he's got a couple other things where he builds this out a little bit more fully. You can take this code and then you can generalize it out to the order to three case, and it's a nice exercise. Okay, so the last thing to talk about is now that we have this T fold, right, or this T product, we can talk about it in terms of the folding and unfolding. Notice that when we actually look at the tensor backpropagation, our operator changes slightly. We're doing 2 unfoldings so that we can iterate over the next step, and we're making use of this B-circulant matrix and a transpose. So there's a few more pieces of minutia that we need to implement, but if we do so, then we get a nice version of this equation here, which allows us to do our forward propagation in a really obvious and clear and straightforward way. Yeah.
Should we just quickly define what B-circ and fold and unfold is?
Yeah, that's a good point. So let's go through B-circ. I have that code. So B-circ, right? Pretty simple. We need a circulant matrix. This was one of the things I was going to add to my slides, but there's a pretty clear picture. So this is a circulant matrix. It's fully specified one vector, which assumes, no, that's not the definition I want. Yeah, so, okay, so it's a matrix where each row vector is rotated 1 element to the right relative to the preceding row vector. So Tim actually, in his notes, he had like a great picture where he showed like the boxes of these things coming down. And that would have been really great to have in the slides. That's what you get for racing to the end. But once we have this notion of a circulant matrix, then
just quickly, Eric, if you just look at the circulant matrix, just in Wikipedia, so the first block is the column on the left-hand side, and then if you kind of transpose it to the row, then it's that bit. And then it's the next column down, then it's that bit, and then it's the next row, and so on. And you see it's kind of diagonally laying out all of the rows in this new form. And it seems like a really weird thing to do, doesn't it? But the beauty of it is when you then take the discrete Fourier transform, it will kind of unravel it again. It's almost like you're putting it in this format where the discrete Fourier transform will,
Yeah, so that's really the reason why you do block circulant matrices. It is literally that. So actually, it turns out this fold and unfold notations, I couldn't find any like examples of this operator being used anywhere, but it turns out that like this is in a lot of ways really helpful notation to give you a sense of how this folding and unfolding happens. So in the paper, they lay out the following statement. And there's not a lot of hints to what fold and unfold actually do. I mean, Tim thought about this for a while this morning. So let me go back up. It's a ways. Unfortunately, transpose. No. Here we go. So the unfold is the first block column. So it's the first block column of this thing. And then when you fold, you kind of do the opposite of unfolding. So we can think of unfold as kind of like Ravel in NumPy. It like flattens things out for us, and then fold like undoes the folding, or undoes the unfolding. So it like refolds it back up.
So I guess given just the block column, the first column, fold actually creates the block circulant matrix for you, correct?
No, so that's what B-circ does. But
that's what B-circ does.
So fold takes in a circulant matrix, does it?
Fold takes in a block column, I guess, because
no, it doesn't. No, sorry. Yeah, so fold just takes in a matrix, which is a three-dimensional matrix. Yeah, I see. Because the
unfold,
thing that
unfold takes
confused me about that is presumably fold of A must contain all of the information in A, because you can then unfold of A must
unfold.
must contain
So,
all the information in A, because when you fold it again, it equals A.
right. So the A superscript 1, 2 through n are what? They're tubles, right? They're essentially
They're tubes, yeah.
they're tubes, right? So the first block column is essentially a vector of tubes, correct? That's what unfold A
Yes.
gives you, correct?
Aren't they?
No, I don't think they're tubes.
Aren't they frontal slices?
Oh God.
Like-
Sorry, I was
slices.
using my mic and then Christian
Yeah.
put it on at the same
Sorry.
time. They're frontal slices, not tubes.
Oh,
they're
sorry.
okay.
Yeah.
Frontal slices defined as follows. Yes, a matrix of frontal slices. Yeah. So this is
Yeah,
sorry. Yeah.
Okay.
So this is a frontal slice. This is a frontal slice. So on and so forth. Yeah. There's still pieces of the notation that we're pulling apart, in case you weren't wondering. I made a best effort, but like this is a dense paper. So okay, so we've got this like B-circ thing though. Once we have a circulant matrix, right? And we apply the I believe this is the Kronecker operator. Yeah, I don't think it's the delta. I think this
Oh,
is.
it's just
I think. Cron. I'm pretty sure it's a product. Yeah, computes the Kronecker product,
Okay.
which does the following. And so, as you can see, so we get this. So ST is something, and then we get out basically an equation from this. So yeah, so this Kronecker gets used over the circulant times the original matrix basically, and we add that to our previous block, and so we get like these frontal slices from the combination of the Kronecker delta and the circulant matrix. Yeah, but so this notation is super handy because it gives us like a semantic way of like thinking about what the hell is happening when you do a T product with all these fast Fourier transforms, because we're in like a higher dimensional space and it's really weird. And so this is a way of constructing and deconstructing things semantically, but it doesn't actually tie to an operator. Unfold and fold don't tie to like standard operators in like any of the frameworks that I looked at. So that's important to keep in mind as well. But yeah, once you've got like a notion of these like different semantics around how to do a T product and everything, then you can. Sorry, I went too far. Then you can define this in obvious terms, right? Like you just get it naturally. You get a lot of things naturally. Sorry, I went too far again. Yeah, you get a lot of things naturally, and you can get the tensor backpropagation and forward propagation in a natural and obvious way. I'm not going to go through how a neural network works because that I feel would take us just way too far afield. But basically, we're just doing forward propagation sends our data forward, and then we update our weights against some loss function, and then we propagate them back. And so the product in normal neural networks is how we pass information forward and back by composing across the layers. So it's the transition between the layers from one to the last.
So Eric, quick question. So on the backpropagation, can you still use the Fourier transform, or do you have to compute that directly? And is this where the leapfrog integration comes in?
Yeah, so we haven't gotten into that yet. So I want to actually motivate the leapfrog integration like a little bit stronger than that, but I think you can say that. I think that makes sense. So you're saying that I have to think about the statement. So you're saying, can you use the tensor product in backpropagation? So we have the formula for backpropagation, right? I think you can use. Well, it's not exactly the T product. It's not exactly the T product, right? Because we have this unfold. So it's not quite the same thing. We're making use of these operators, but I think the fast Fourier transform and the inverse fast Fourier transform are still hidden in the weeds. Again, I did not implement this piece, so I don't know. But like, this is my suspicion.
Yeah, because before it was the circulant matrix times the unfold.
Right.
And that was kind of equivalent to the Fourier transform, but this is different. This is two unfolds, and then you're taking the sort of element-wise product in the middle. So I don't know. It just seems to me that maybe this is a little bit different. So when you're doing back propagation, you can't use the same computational trick. Maybe I don't know.
No, so you can't use the same computational trick, but I think the unfold is doing a fast Fourier transform underneath the hood. Like I think that's what it is. I think.
Don't think so.
Oh, right. Okay, so that's what you're saying. Yeah. You're right. It's probably not the same computational trick. I'm sorry. I was saying things that are not true. I apologize. Lies. Bad. Lies. Okay, so you can't actually. This is the section of the paper that I did not internalize. Everything else I get. This is the only thing I was like, fuck it. I'm not gonna actually do anything. And now here we are. So, yeah. So I'm not actually sure how we do the back propagation. Yeah. This is like the problem is I don't know what unfold does still. Like I kind of get it, but I still don't know. And so like, is it just a tubal slice that's weird? It's unclear to me. But this is, I think, the missing piece for me still. So I'm just going to leave this. I'm going to lay this at everyone's feet. I mean, you can do this thing, but like, who knows what the hell this? I'll lay this at everyone's feet and just say I'm going to throw my hands up. But I can talk
Shall
about
we?
stuff.
I
Yeah.
was going to say, just with an eye on the time, shall we just get to the results of the paper? And
Well,
because I think the results are really quite exciting, and this is a
one more
brand new
thing.
paper.
Please just let me do this last little bit, and then
Okay,
we
go
can
on.
right to the results. Okay. So this is the last thing that I want to talk about. That's really cool. So it is this statement: discrete neural network is a discretization of differential equations. This is a big deal. Now, this is not the paper that lays it out. Obviously, it's laid out in 8 and 9, but this is a pretty recent result from that standpoint. So the reason why this is huge, sorry, I have notes on this. We've gotten so far off of my original notes. I have to figure out where I am. But let me just do that really quick. I want to do this little rant, and then we can go on to results. So this is a big moment. It's been around the literature for a little while, but truth be told, this is the first I'm hearing of it. This connection between differential equations and neural networks is a big deal. This is the theoretical lens which we can view all neural network architectures. And honestly, it should be obvious because what is a neural network, right? It's a derivative, in this case a chain rule, taken over a vector space. And that sounds like a differential equation to me, but I never really thought about it before. And so this allows us to take advantage of the century-old tooling of differential equations for free, which is why we can use the leapfrog, which we're going to see in a little while. But we get to use it for free. And unsurprisingly, this is what we already kind of do, right? We look at how neural networks converge according to some measures. So this connection makes a ton of sense. But we now can also look at the theoretical implications with respect to stability in differential equations.
So Eric, I can certainly see the connection to differential equations. What does discretization mean in this context?
So
I think it means that differential equations are continuous.
Yes.
And this paper uses the word mimetic a lot, and I didn't have a clue what it was talking about. And we were googling around, and I think it literally means kind of when you discretize a continuous, differential equation, what you're doing is you're kind of mimicking it with an algebra. I mean, for example, with Euler integration, you're kind of mimicking you're mimicking a differential function, but it's not quite the same. So that it uses this mimetic linear algebra kind of jargon, which didn't make sense to me.
Yeah.
Okay.
So
is it more like, instead of taking an analytical approach to solving a differential equation, this sort of mimics a numerical approach?
Yes, exactly.
Okay.
Yeah,
So
exactly.
All right.
But we can make use of numerical methods from differential equations when we can't approximate it analytically. And so now we have the whole toolbox of differential equations and numerical methods. I mean, we sort of had that already, but now it's like clear and there's an obvious and clear connection. And honestly, when I was in graduate school, I think this is the thing we were looking for more than anything else, because there was no theoretical motivations or housing or couching for neural networks at all. And now we have this. This is a really big deal. For all of those reasons, now we can think about it from a theory point of view. We can extend things in obvious ways. And now neural networks are just another toolbox in the numerical methods suite of tools. And that opens up a lot of areas of research in a lot of important ways, in like true science. So I don't know. All right, I'm done yelling about that. Now we can go on to the results. We're going to skip over the Hamiltonian stuff because whatever. So leapfrog is a technique from numerical methods. I don't have time to go over it just because we are pretty close to the end here. I mean, we're already half an hour over, but like, I have a quick little thing that you should look at. I'm going to post this markdown file since I didn't get the slides all the way done, but I'll post this markdown file somewhere. So just to show you really, really, really quick how leapfrog works. So we can start with some harmonic oscillator, right? And this is what the leapfrog does. We start with x0, and then at t1/2, we do this, and we just sort of leapfrog forward, and then we end up at t1, and then we approximate at t3/2, and so on and so forth. We can write a simple Python program to do this. Hooray! And it turns out that we can simulate the stability of a spring, and we can look at how things converge over time. This feels like the same analysis that you would do in a neural network. At least this part does. So there's an energy loss for these things unless you basically take away all the damping and so on and so forth. And we can see how power comes into this and so on and so forth. It's not super important, but like that's what's going on when they do the leapfrog thing. So here are the equations for it. I highly recommend reading this. It made things very, very clear. I did not understand what was happening based on these equations. And so we can get to our results. So with the leapfrog, that's C here, and with an H of 1, H is a tuning parameter within the model. We can see that here.
It might just be worth just quickly saying here that on Euler integration, all you're doing is you have some kind of a function, and you need to discretize it, and you need to have a kind of step in time, and you need to say what is it going to be at this step and this step and this step. And the problem with Euler integration is you get all of this kind of numerical divergence. Numerically it's very, very inaccurate. So leapfrog is just a way of kind of predicting all of these discrete points in time for this function with increased accuracy. If you've ever done any 3D graphics programming, you might have heard of RK4 integration, for example. There's lots of different types of integration.
That's super helpful. Sorry, I thought everyone just knew Euler stuff, so I just skipped over it. That's bad. All right, anyway. So we can see that the Euler doesn't really converge, but we get nice linear separability for the leapfrog with 32 layers. And this is actually a really big deal. The fact that we're getting linear separability is essential for accurate classification. I'm not going to go through why linear separability is important, but it's a big deal.
And just quickly, what is this data that we're separating?
So
I think didn't they generate some random?
Yeah, they generated some random points.
And they had some concentric circles, right?
Yep.
Which
Sorry, I have another question here. So I see the input data is in R3, right?
Yep.
So that's what. Okay. Yeah. So stupid question, but for a tensor network like this, does it only make do we only get the benefits if the input data is higher than 2-dimension, or all of these generalized?
We tested on Saphir and we tested on.
Okay.
Right. But that's a very good question, Jit.
Yeah, it's a super good
question.
But
I believe it does still find high dimensional latent representations, even because in an image, of course, you have hundreds or thousands of dimensions, and it still seems to find some kind of latent representation.
Right.
But I think they actually go on here to test it on MNIST and to test it on CIFAR10, which are two of the most popular vision data sets.
Yep.
And it's essentially using something like a densely connected network, but of course, with these tensors on the layers. And as you can see on this method, on MNIST, I don't want to take the words out of your mouth, Eric, but it's converging significantly faster and it's performing better.
So some things to note. They actually try this for matrix to matrix products in three space. So they define an M product and M back propagation, and they define all the theoretical rigor around numbers that you need to care about and everything. And it turns out that where's the Saphir one? No, I think I passed it. Well, it turns out that the vector to the 1D vector to matrix product, the T product, does the best. So we have this red line here, right? T 10 8 does the best. It approaches the fastest, right? It stays consistently lower, and it gets the best performance. So this fat representation that we have with matrices doesn't even do as good as the thinner representation. And this is like a surprising result, and it's a big deal, and this is why this paper got published. Yep, that's basically the highlight. So T neural networks. I'm going to probably make an implementation this weekend, and then I'll be passing it around on the machine learning channel if anyone's interested.
And this is kind of huge, right? Because the biggest problem with neural networks is just the amount of computation that's required and storage requirements and so on. And this seems to this just seems to perform so much better with an order of magnitude less computation required. And somehow it's working on vision data sets. It's just kind of mind blowing. But anyway, we're nearly at the 1 hour mark. So if anyone would like to leave, feel free to leave. But any questions are welcome. And I just want to say on the recording, Eric, thank you so much for this presentation. It was absolutely wonderful. You set the bar really high, but I don't want to intimidate people from coming forward in the future to doing presentations, because I think this was actually quite a mathematically advanced presentation. And I expect this will be one of the more mathematically advanced presentations that we'll have. So don't let this put you off in any way. You don't need to go to the level of depth that Eric has. I hope in the future that we'll have lots and lots of people doing talks on papers. But anyway, with that said, any questions, guys, please go ahead.
Yeah,
comments though. Eric has motivated me to grit my teeth and go through the paper now.
Yay!
Brilliant.
Despite all the
I've
pain
succeeded.
that I'm absolutely certain to face, but
I've succeeded.
I'll do it.
Yes, math is good for you. It's like brushing your teeth, but it feels good. Okay, anyway, sorry.
Yeah, I had a quick question. This is more about sort of general approach to internalizing literature like this.
Yes.
So when going through this, I started off and very early on in the intro, it says that this work builds on work presented in another paper. So then I jump to that paper. Then that paper says, okay, for our discussion, we based it off of the presentation of like a ResNet. So then I jump, I'm reading about ResNets, right? Which is like, it's all like certainly valuable learning, but do you have any tips on like how deep down the holes you should go? Because I mean, in this paper alone, there's like 10 different, really complex things that you could, spend a year on.
Yeah, so you could easily do that. So my advice to reading a paper is actually to read it in its entirety first. Just because they give you the advice that they based it on something else doesn't mean you should necessarily jump and go do that. Actually, I think I have it in here. Yeah, so this paper, most of it's well motivated, actually, in another paper by one of the authors. So there's 2 other authors on it. This is a fun trick. You can actually look at what the author did in previous things. I think this is probably the thing that motivated me the most. So Misha Kilmer is on both of these, and this I think pretty much lays out more or less the same paper. Eventually, this stuff all kind of bleeds together. You really only need to understand it once, but they go through like the matrix, the circulant matrix, right? There's a new vision of tensors. They talk about the mappings. They go through like all this stuff. Where is it? They talk about tubles, right? Like, oh, okay, we did tubal things. Like the only thing that's kind of missing from this paper, they do SVD, right? So they define another tensor thing for SVD, in this case, single value decomposition, and they actually look at invertibility like really closely. But the point here is that like this paper is very similar to that one, and I just kind of like, while I was trying to internalize some of the pieces of this that I think were not laid out super clear, I went to that other paper that the other author wrote. So something to call out about researchers. When they write a paper, right, they are doing a continuation of a body of work that they started a long, long time ago. And so if it feels like they're hiding a lot of details, it's because everything is so obvious with them, because they obsess and obsess and obsess and obsess over the content. And so if you want to see like a basic introduction to the thing, it's actually easy to start at T timestamp 0 for that researcher, and then go up to TN if you really want the full like thing. But I think that's unnecessary. I think the right thing to do is to start at the paper, and then honestly, Googling around for individual pieces that you don't understand is going to be much better than reading like 50 or 100 papers. You should at most probably have 5 reference papers for any paper that you're reading. And if you've done more than that, you've done too much work and it's just going to overload you. When you do a research paper, you should meet it where it stands as much as possible. If you really need to look up a lot of the primitives, then a textbook is a far better resource than reading the other papers associated with it, because those papers are intended for a PhD level audience that already has done this stuff so much that they're actually bored with it, right? For people like you and me that are out in industry, like we're not talking about this stuff all day. We're not thinking about this for 17 hours at a time, like 6 to 7 days a week. And so,
just a quick counterexample to that though, because it's tempting to go and pick up a textbook or something like that, and you can just go down the rabbit hole on linear algebra. And what's great about papers is they'll show you a concept, and it will be a direct application of that concept, and it's almost everything you need to know about that concept. And there's a lot to be said for, as Eric was saying, going through the paper once, and really reading the abstract and the conclusion, and just setting a mental frame for what you have to learn. Because if you do go outside, you could really go down the rabbit hole, and you could get lost, and you could never find your way back. But I appreciate as well, by the same token, that usually in papers that every concept builds on the last, and if there's something that you fundamentally haven't grasped, you might get stuck in reading the paper. So sometimes you'll need to go out. I think the answer is it depends. I think it depends very much on the kind of person you are.
I'll also give another example in support to what Tim just said. A concrete example. When I first read the RCNN paper, I didn't know what selective search was. And to be able to figure out how those boundaries actually define things and how things are, I needed to go read the paper on selective search. It was. So to some extent you can accept facts and move on, just accept the results that come from other papers and say, yeah, somebody must have done a good job there and those must be true. But sometimes reading other papers are absolutely mandatory, because you otherwise you won't make head or tail of what they're saying in this paper. So yeah, it's unavoidable, I guess, the rabbit hole to some extent.
Yeah.
So counterexample to the counterexample, you can also use things like Meta Academy.
That's
demonstrated tensors. So this is really good. Another thing that Jit and I talked about when we were having pre-conversation about one of the other talks I gave on Friday, which feels like forever ago. The PyTorch documentation is super good. And they explain, you get an implementation. So let's just pick something random. You get an implementation, but you usually get, no, this is a bad one. I need opt maybe.
Go to like say an embedding layer or a convolutional layer, and you want to show the math, right?
Yeah, I want to show the math convolutional.
Yeah, so you just go to torch NN, and then just go to, say, the convolutional layer or an embedding layer. On the left, to your left in the menu, there is.
Okay, convolutional.
So the example I was giving Eric earlier was that I always forget the biggest mistakes I make is with shapes of things that go in and come out, right? I never remember the formula, like, okay, what's the padding, how many, filters, etc. And the PyTorch documentation is the best that I've seen in combining actual technical documentation with the math behind it. So I look at those formulas, like L out, it tells me that's what it's going to be if I put in padding of this much, and it's right there. I don't have to go look at a paper or a book or anything.
Yep. And then the final thing I would recommend is glossaries. So this is the one for topology. This got me through my topology class. I literally needed this every day because every single homework assignment, there's so much shit. But like, it gives you these one-sentence descriptions. There are equivalent glossaries for algebra, right, which is what gets used a lot. Oops, damn it. Glossary. There are equivalent ones for algebra, which I don't have as handy for some reason, but glossary of mathematical terms. Okay, this one's like kind of okay. There's a better one that I stumbled upon once upon a time. But yeah, so there's good glossaries for abstract algebra and for all these other things. The topology one on Wikipedia, I think, is my favorite one. But so as much as you can, making use of things like this is really helpful. But yeah, okay. Do you feel like we got a full answer? I'm gonna stop sharing my screen. I don't care anymore.
This was awesome, by the way, Eric. Thank you so much. It was
Yeah.
absolutely phenomenal.
Well, this was super fun. I had a lot of fun reading this paper and like trying to internalize it. It was.
I just feel like I need a lot of caffeine after a class at the uni. I went back 25 years. It was hard, but hey, it was awesome.
Yeah, it's the same sentiment for me, Eric. It's been an absolutely fantastic call, and I think don't shy away from it's going to be hard, but it's going to be worth it because we're going to challenge ourselves every week, and I think it's really going to help us up our game. So don't in any way feel embarrassed or anything like that. We're here to learn. It's a positive environment, and Eric, thank you so much for setting the bar so high on the first call.
Parting comment, Tim, as an organizer, I don't think your original estimate of 30 minutes is going to work for pretty much any of our meetings.
Well, I'm conscious. I'm conscious of people's time, so I think what we should do is say that it's almost like concentric circles of complexity. So the first 20, 30 minutes is about really high level. I think we should have a bit of structure in terms of what are the key findings of the paper, what is this paper all about, what's the context of this paper, why have I selected this paper, and then if people want to hang on the call, and of course we'll record the call and people can watch it later, then we'll kind of go into the detail, and I think that's kind of what we did anyway.
Yep, fair enough.
Great. Okay. Well, if there's no more questions,
run, guys.
Thanks, guys.
Awesome.
Thanks,
Have a good one. Bye.
See you later. Thanks again.